Hi everyone, I'm Daniel, and today I'm going to talk about a massive southern ocean phytoplankton bloom fed by iron of possible hydrothermal origin. And it's an article from the Nature Communication. So first, I want to talk about the basic knowledge you need to know and the research motivation. So first, how does the dissolved iron impact on the ocean? So we all know that nitrate, phosphorus, silicon are the basic nutrients that when the phytoplankton grow. So besides of them, there are still some trace elements like iron that is important for the phytoplankton to grow. Without them, phytoplankton can't grow well. So second, let me introduce you the environmental conditions of the Southern Ocean. The seawater in the Southern Ocean is laid on the iron. So the phytoplankton bloom there is not a common phenomenon. But recently we find a bloom on the Southern Ocean that almost appears every year, and this is what makes us curious at. So first, let's take a look on the geographical location. So here's our research location. So it's between the Australia and Antarctica. Let's look closer, and this is the geographical location, and you see the orange line and the red line here. There are two hydrothermal vents, which is KL2 and KL1, and this white dash line are the southern Antarctic circumpolar currents, and this one is the southern boundary of Antarctic circumpolar currents. And let's look at this. This is the Mainland primary productivity map. So you can see in this area, their mean MPP is higher than all the other around. So this is the place where the bloom appears at. And let's look closer. And in this graph, this is the orange line and the red line are the hydrothermal vents. The purple line and the pink line are the SPSCC and SCCF. This gray line is our cruise, and the white arrow line are the current flow. And at this picture of satellite picture, you can see this is the chlorophyll A concentration picture, and display is where the bloom is, and all the numbers here are our sampling station. So here's our guessing. Do the vents supply something important to the bloom? Because we all know that the bloom in the Southern Ocean is not a common thing. And why does the bloom appear there? So first, let's look at these four pictures. First, let's look at picture A and B. It's a picture of concentration for chlorophyll A and POC. You can see the concentration here is very high. That's because of the bloom. And let's take a look on the picture C and picture D. You can see the nitrate. On the surface water, the concentration of nitrate is very low because of the phytoplankton use the nitrate. And so does the diffusion iron. So you can see the surface of diffusion iron is very low, but there are something anomaly different. You can see that in this area under the bloom, the diffusion iron here is very high, and it's an important part, and I will answer you why does this happen after. So let's first take a look at this picture. The white line here, is a depth, and the X line is the concentration of diffusion iron. So first we can know that first diffusion iron is high when the depth of deep, but whether the depth at. And at this part, we can see that the diffusion iron start getting difference. And at this part, we can see that the diffusion iron will get low. Oh, sorry, I didn't mention the green line here is the station where within the bloom, and the gray line and the black line here is the station which is outside of the bloom. So we have to determine whether the chlorophyll of the iron is support the phytoplankton inside the bloom. So let's look at the station within the bloom. The diffusion iron to POC accumulated range. Inside the bloom, the range is 4.0 to 5.2 mmol per mole, and which falls into the range of the P Antarctica, which diffusion iron to POC accumulated range is 2.3 to 8.6. And this kind of phytoplankton is a dominant group in that area. And the station outside of the bloom, the diffusion iron to POC accumulated range is not falling in the range. So we can know that the chlorophyll of the iron is significantly supporting the phytoplankton inside the bloom. So back to the gassing, we know that the band really supplies something important to the bloom, which is iron. And then let's go back to this image. We can see the bands here, right? So, but the bloom appears here. And we're guessing it's because the current and the bathymetry. So let's take a look at this picture. The water edge at this area, these events, and we can see the water mass is younger, and in our data it's colder and fresher. So let's look at the data. The upper one is agnic energy, and this is net primary productivity, and this one is bathymetry. So let me explain why. So this is the Antarctic current, the Antarctic circumpolar currents, you can see. And this is the bathymetry. So when the current flow, and because of the bands, the bathymetry is getting higher, so it causes the upwelling. So the upwelling water will bring the diffusion iron up on the surface, and you can see because of the bathymetry, the energy is getting lower, so the flow getting weaker, and the iron can accumulate it here. So it causes the bloom. So back to the gassing, we know that the currents and the bathymetry play an important character. So based on conclusion and future prospects, we know that the bloom is caused by Cal1 and Cal2 hydrothermal bands, which provides the diffusion iron. And the currents and the bathymetry play an important character to push them together. And yet, the consistent location and productivity of the bloom has apparently made it a hotspot for upper trophic level activity. Furthermore, in other research, we find that whales visit the region of the bloom, suggesting well-established migratory pathway and persistent use of this feeding ground. So, furthermore, the bloom has implications for conservation efforts in this region. The Ross Sea Marine Protected Area covers a few small portions of the bloom region, as you can see here. Here. But you can see it didn't cover the whole region of the bloom. So this is something we have to improve. And yet, the bloom is important to the upper trophic level, and it's a potential CO2 sink. But the region of it is decreasing rapidly, result of the climate change. As you can see, the region of the bloom is decreasing yearly, and we have to make change quickly to save this bloom. So here's my presentation. Thanks for listening.
Why in the last slide and the land, I think ice is different years by years.
Repeat.
Is that like you say you think the ice increases yearly? Is that what you mean? Okay, that's not the ice. That's because this is the satellite picture, so it's because of the cloud. Yeah, can you understand? Yeah, it's because the cloud that covers, so the satellite can take the clearly picture. So yeah.
Patrick.
How much concentration of chlorophyll A you count as a bloom?
Oh, you mean how much concentration of chlorophyll A that I call it a bloom? So sorry, it didn't mention in the article, but I think it should be just like on the image for like 10 microgram per cubic meter.
In your research, you say the well will visit the bloom region, right? So, and the bloom region will change every year. So, did the well also change?
You think it's because the you said that the region of the bloom will change every year, so you think the whale's migration pathway will change every year, right? So I think it's possible because the bloom will change every year, but basically the whale will go to the area for about every year. So it's okay for the bloom to have change. But if the bloom get totally decreasing, and I think it will be dangerous for the whales.
Can you show the slide that have a GIF?
Oh.
Yeah. Yeah. What kind of the climate change will affect the bloom?
Oh.
Yeah.
Okay, you said that what kind of climate change will influence the bloom, right? So, because bloom is basically it's because the phytoplankton there growing well. So I think it's a lot of condition that will change the bloom. So like temperature or salinity, and that's all can be the condition to change the bloom.
We know the hydrothermal vent not only product the iron, but we will have another poison element. So why the bloom will not affect by those poison elements?
Repeat.
You said that the hydrothermal not only produce the iron, but it will produce other elements that might be poison, right? In my article, we don't know. We don't do the research in this area, so I can't tell you. Sorry.
Yeah.
Where is the depth of the EKE you calculate? Because the EKE depth higher than the ridge is not the well data you can use. Because EKE is focused on a layer, not whole water mass.
Repeat.
You said that where I calculate our EKE data in depth, right? So I think our data is on the surface, but I can in our research we didn't mention that much. But I think it's because the warm water and the pressure. So we'll due to this conclusion.
It's a very interesting talk, and the story itself is very interesting. And so let's talk about some nice part of his talk. This table is actually quite interesting. So I don't remember if it's in the paper, but yeah, okay. Nicely made, okay. And the other thing is, I have to say this conclusion is very specific. So based on what I have seen so far, it gives you very specific conclusion, nicely summarize what he has presented, instead of some general comments which you would know without reading the paper. So it's a very nicely made conclusion, and this also, yeah, sense of style, yeah, as said. Okay, and his presentation speed is also nice, but what can he improve? So the first thing is, first of all, although it would be nice if you say shortly regarding how the data were collected. There, you didn't say anything like, I'm sure there was satellite data and also CTD data, but you said nothing about this. It would be nice to have show 1 or 2 slides talking about this without detail. Maybe just show keywords. And then the next thing is many of the figures were not introduced. Like this is actually a very, very busy figure with 4-parameter multiple stations and also over depths. This is actually a complicated figure. So as we said, how to present a multi-panel figure? First, you show a very large figure and use it to introduce it carefully. And in addition, you have to pay attention. So for those who have the same situation, please remember these numbers have no meaning to us. In order to give the meaning, you have to show the map next to the station like what you did here. Otherwise, we have no idea what you are talking about. Where is the transect here? All right. And this table was nicely made. However, what was unclear to me is why would you would like to compare the is it diffusion ion to POC ratio? What's the meaning of that? You don't have to explain it here. I think this is missing. Maybe you have said that, but if you did not print keywords here and just quickly go through its meaning, you left no impression to the audience. And considering that you spend some time comparing the numbers here, you should first tell us why you want to use this ratio. Use one slide to explain it. You have enough time. And another thing that was missing is, I like the way you present here. However, I was waiting and hoping you can explain this EKE. However, you did not. I don't even know if you have read its full name, or you assume everybody in this room know what EKE is. So, if you want to explain this, I assume this is important. Then you should also again spend one slide explaining this. And furthermore, this figure is distorted, 扭曲的. I actually cannot read EKE when I was standing there. If you want to show it this way, you have to make the label again yourself, because I cannot read it. There, back there. All right. And lastly, it's nice that you presented this future prospect. However, I noticed that when you have done nicely over the talk, however, at the very end, I saw you were doing this. You were, you know what I mean? That, yeah, so considering the way you deal with QA, I'm sure you will be able to do that like without really having to look at your smartphone. So next time, I hope to see your improvement in this aspect. But overall, it's a very interesting talk. Let's thank Daniel.